So in the previous video, we talked about the half-wave rectifier with RC load, and we saw some important equations. We saw that the output will appear like this, will appear as increasing or charging of the capacitor, and then discharging, charging, discharging. During the charging, the diode will be on. During the discharging, the diode will be off, and so on. We defined the maximum or the peak of this voltage to be V output peak, and we found the relation between V output peak and the peak of the input, peak of the secondary voltage, to be V secondary peak minus V diode, okay? And we defined the variation in the output voltage to be called V ripple. So V ripple is the difference between the maximum and the minimum of the output voltage. And we defined the average level or the average of the output voltage to be V output average to be V output peak minus half of the ripple. V output peak minus half of the ripple. And then we said that it's important for us to calculate the ripple voltage. We calculated the ripple voltage using some approximations, and we found that the ripple voltage will be V output peak over multiplied by T over RC, or you can say it's V output peak over F RC, where F here is the frequency of the sinusoidal wave. It's 1 over the period. And also we calculated the conduction time, delta T, this conduction time where the diode is on and the capacitor is charging, and the conduction interval, the conduction angle, okay, theta, that is equivalent to the conduction interval. We calculated delta T to be 1 over omega square root of 2V ripple over V source peak, and here use the peak of the secondary voltage or the input voltage, and theta, the conduction angle, will be only the square root of 2V ripple over VSP. So you have to be careful where to use V output peak, which equations use V output peak, which equations use VSP. These equations are very important to calculate all the parameters required for your rectifier circuit. Let's now solve an example, and then we'll go back to our circuit and calculate the peak inverse voltage, and we'll discuss some issues about the current. So the example says find the peak DC output voltage, peak output current, ripple voltage, conduction interval, conduction angle. So basically everything about our rectifier. Given data, secondary voltage of the transformer, this is what we call Vs, as 12.6, but it's given as RMS. So this is Vs root mean squared. It's 12.6. 60 Hertz. So F, the frequency of the sinusoidal wave, is 60 Hertz. So this is how I'm writing the equation. I'm writing the information given. R is given to be 15 ohm, C is given to be 25,000 microfarad, 25,000 microfarad, okay? VDO is 1. The voltage drop across the diode is given as 1, and it didn't mention anything about the resistance of the diode. That's why implicitly it means that you consider the diode to be a constant voltage drop model. You will use the constant voltage drop model to represent the diode, because if it wants you to use the piecewise linear model, it should have mentioned the value of the resistance of the diode, RD. But since it didn't mention what is RD, then you use the constant voltage drop model. Now this is the information that we have. In our equations, we don't have the RMS value of the secondary voltage. We have the peak of the secondary voltage. That's why you have to convert this value to the peak. So you have to say that Vs peak equals, what's the relation between the RMS and the peak? The RMS is the peak divided by square root 2. Or the peak equals the RMS multiplied by square root 2. So the peak here will be 17.8 volt. This is VSP. The peak output voltage, The peak output voltage, what is the relation between the peak output voltage and the VS peak? V output peak equals VS peak minus VDO. So it's 17.8 minus the voltage across the diode, which is given to be 1. So it will be 16.8 volt. So we calculated the peak output voltage. From the peak output voltage, you can calculate the peak output current. The peak output current is the peak output voltage divided by the resistance. The peak current, or the peak output current, is the peak output voltage divided by the resistance. This is the maximum current that will go to the load, right? And it will be V output peak divided by R, 16.8 divided by R, which is 15 ohm. This will give you the peak output current to be 1.12 ampere. Then we need to calculate V ripple. So in order to calculate V ripple, we go back to the equation. V ripple can be calculated from V output peak, from the frequency, from R, from C. We have all this, right? So we can calculate V ripple as V output peak, which is VS peak minus VDO, multiplied by T, which is the period 1 over F, divided by RC. We'll be able to calculate the ripple voltage to be 0.747 volt. The conduction time and the conduction angle, the conduction interval and the conduction angle can be calculated again from square root 2 V ripple over VS peak. Okay, and again we have V ripple. We already calculated V ripple from the step before, and VS peak already we calculated to be 17. Calculated VS peak to be 17.8. Okay, so we substitute here 17.8 and V ripple we substitute it to be 0.747. You will be able to calculate the conduction angle in radian. If you want to convert it to degrees, you multiply by 180 over pi. Then the conduction time, or the conduction interval, is the angle divided over the angular speed. It will give you the conduction time to be 0.769 milliseconds. So this is an example. I'm giving you all the information, and I'm asking you to calculate the parameters. V ripple, V output peak, the average of the output. In some other examples, I will give you the design parameters. I want V ripple to be so. What should I choose for the input voltage, for example? What should be the frequency? What should be the value of the secondary voltage? What should be R? What should be C? So you have to connect all this through the group of equations here. These equations will help you to design any half-wave rectifier. Now let's go back to our circuit and talk about the peak inverse voltage. The peak inverse voltage for our circuit, let's plot the circuit. This is our circuit with RC load. This is VS, C, R, and this is VL. In order to calculate the peak inverse voltage, as we agreed, where is the voltage of the diode? The voltage of the diode is this. This is the voltage of the diode. Where is the inverse voltage or the reverse voltage of the diode? Let's call it Vx. It will be in this direction. This is the reverse voltage of the diode. The voltage put in the reverse direction of the diode. So Vx, this is the reverse voltage of the diode. Right, let's write a relation between Vx, Vs, and V output. We can say here that Vx equals V output minus Vs using Kirchhoff voltage law. Very easy, direct. So Vx equals V output minus Vs. The question here, when the diode is off, because we are talking about reverse voltage, right? The maximum reverse voltage on the diode. This means that you are discussing the case where the diode is off. So you have to assume that the diode is off, and you calculate the maximum inverse voltage of this diode. So when the diode is off, what is the peak of this? What is the maximum of this? This is the peak inverse voltage. So the peak of this happens when the output is maximum and when the S is minimum. So the maximum of Vx, it happens when this is high and this is low, right? At the maximum of V output and the minimum of Vs. So we can say that the peak inverse voltage, it happens when V output is peak and Vs is minimum. But what is the peak of the output? The peak of the output, and here because we have a capacitor, so the output can remain charged, right? Even if the diode is off, there can be a voltage at the output due to the charge of the capacitor. The capacitor will be charged to V output peak, right? So the maximum of the output will be V output peak, which is V output peak can be written as Vs peak minus VDO, right? This is V output peak minus. What's the minimum of Vs? What's the minimum of Vs? Vs is a sinusoid. Vs is a sinusoid, right? That goes from Vs peak to minus Vs peak. What is the minimum of Vs? The minimum of Vs is minus Vs peak. So here the minimum of Vs is minus Vs peak. So here the peak inverse voltage, the peak inverse voltage will be 2 Vs peak minus VDO. As you see, when you compare this peak inverse voltage to the peak inverse voltage of the previous circuit, you will find that in the previous circuit, the peak inverse voltage was Vs peak minus VDO. It was Vs peak minus VDO only. But here it's 2 Vs peak minus VDO. Why is that? It's 2 Vs peak minus VDO because the capacitor now provides more voltage in the reverse direction. When the diode is off, the capacitor is trying to push current. It provides an opposite voltage, a reverse voltage of the diode. This reverse voltage provided by the capacitor increases the peak inverse voltage from being Vs peak minus VDO to 2 Vs peak minus VDO. That's why the peak inverse voltage in this circuit, although this circuit is useful, it gives us kind of smooth output, but the peak inverse voltage is higher, which means that we need to choose a diode that can withstand higher inverse voltages, that will not break down for higher inverse voltages, okay? So here, in this circuit, the peak inverse voltage will be higher than the previous circuit of resistive load only, and the peak inverse voltage will be 2 Vs peak minus VDO. Okay, great. So what about the maximum forward current? The maximum forward current is very difficult to calculate here, because when the diode is on, if you assume it's a short circuit, or even you assume the constant voltage drop model with a battery, both the resistor and the capacitor, they are going to take current. And it is very difficult to calculate at which moment this current will reach its maximum. The analysis here is a little bit involved. It's provided in textbook, however, this is outside the scope of our course. That's why we'll not go into this depth of analysis, and we will not be able to calculate in our course, we will not be able to calculate, or we will not calculate the maximum forward current for all the rectifiers, whether half-wave rectifiers or in the future when we study the full-wave rectifiers, we will not calculate the maximum forward current for those rectifiers that have RC load. So any rectifier that we'll study, with a half-wave rectifier or in the future full-wave rectifier that has RC load, we will not calculate the maximum forward current. However, we will calculate the peak current in the load. Will be interested to calculate the peak current in the load, which can be calculated as V output peak. So the peak current in the I output peak, the peak current in the load can be calculated as V output peak over R. And then V output peak can be related, we can find the relation between V output peak and Vs peak depending on the model. For example, if you assume ideal diode, then V output peak will be the same as Vs peak. This is in the case of ideal. In the case of constant voltage drop model, V output peak will be Vs peak minus VDO minus the battery voltage here, okay? And in the case of piecewise linear model, V output peak will be Vs peak minus VDO, and then multiplied by the voltage divider, multiplied by R load over R load plus RD. So we'll be able to relate V above peak to Vs peak in any of the models that we studied. Also in the future, we will get some circuits for the full wave rectifiers with 2 diodes in the path here. If we have 2 diodes in the path between V above peak and V above peak, if we have 2 diodes, then this is V output, this is Vs. Then the relation, again, the peak load current, I above peak, will be V above peak over R load. Remember this, we'll meet this circuit in the future when we study something called the bridge full wave rectifier. We'll have 2 diodes. We'll have 2 diodes in the path. Okay? In this case, V above peak will be equal to Vs peak in case of ideal, but in case of constant voltage drop model, V above peak will be equal to Vs peak minus 2 VDO. Why 2 VDO? Because we have 2 diodes in the middle, and if we have the piecewise linear model, then we'll have 2 resistors. Here, RD, RD. In this case, V above peak, in the case of linear or piecewise linear model, it will be Vs peak minus 2 VDO multiplied by R over R plus 2 RD. Okay, so this will be the relations in case of we have 2 diodes in the middle, and this example will meet in the bridge full wave rectifier later. If you have only 1 diode, then you can relate V above peak to Vs peak using these relations, and then use it to calculate I above peak, which is the peak current in the load. But the maximum forward current, let's go back to the maximum forward current. The maximum forward current, it will be difficult to calculate in all circuits that contain RC load. RC load. Why? Because the analysis will be a little bit complicated, because you have to take the current in the capacitor into account, and the current in the capacitor is C dV by dt, and you have to go into the relations and the differentiation of the voltage with the capacitor, so it will be kind of involved. However, I added 2 slides here for your information only. They are not included in the exams or anything. This is for your information only, to show you that the current that the capacitor will take actually in practice will be very high. Why? Because the capacitor discharges over long interval. Over a long interval, the diode will be off, the capacitor will discharge a huge amount of charge, then it will charge the same amount in a very short interval. When the capacitor charges in a very short interval, in the conduction interval, the capacitor is going to charge, and it will charge the whole thing that it lost through this long interval. So it discharges over a long interval, and then within a short interval, it should get all the charges that it lost back. This causes the current of the capacitor during the conduction interval to be very high. It can reach to 48 ampere in this example. In addition to that, in practice, when you first turn on the circuit, because you are connecting the source to the capacitor directly, you are connecting the source to the capacitor directly, and between them only the diode, and if you assume ideal diode, this diode will be short circuit, then the current of the capacitor can be written as C dV by dt, and V is the secondary voltage, which is V's peak sine. If you do this differentiation, you will find that in the beginning, at t equals 0, when you first switch on the circuit, the current of the capacitor will reach a very high amount. It can reach, in this example, to 168 ampere. That's why, in practice, we have this surge current that appears at the beginning, and the other current that appears periodically to charge the capacitor with high values. This is only for your information. However, in our course, we are not going to do this kind of involved analysis. It will be enough for us to calculate the peak output current, the peak current in the load, which is V output peak over RL, And as I explained here, you can calculate the output peak and relate it to VS peak from these relations in case of you have one diode only like in the half-wave rectifier, or in case of two diodes like the bridge full-wave rectifier that we'll study later. Okay, that's it for this video, and see you in the next video inshallah. Assalamu alaikum.